project of my title is Generalized ML-based Pluvial Flood Risk Mapping in the Regional US. So why is flood prediction a problem? Over the last 30 years globally, it's caused the deaths of 200,000 people and caused severe economic damage. Unfortunately, climate change has exacerbated this problem. There's been a 150% increase in Northeast US flooding since 2000. That's why we need better prediction mechanisms that can help us identify the areas that need flood mitigation strategies. Current methods to predict floods are pretty fragmented. For example, FEMA flood zones are used nationally to identify flood insurance for households. These use physics-based equations to identify which areas are at risk and are static, which means that they don't change based on climate conditions. On the other hand, Google Flood Hub uses machine learning to predict river-based flooding around the world. My project addresses a critical gap in the literature by first looking at a monthly to yearly time frame, which gives a significant amount of time for disaster lead time. And additionally, it combines the predictive power of ML with physical equations to make sure that these predictions are physically consistent. Therefore, my proposed hypothesis is ML-based modeling of static and dynamic climate data to forecast monthly to annual pluvial flood risk improves prediction over current approaches. I bolded a couple of words that are important. So first of all, static and dynamic are the two types of data. Basically, one is unchanging. Think about things like elevation or land terrain. Dynamic variables change over time. This is things like precipitation and runoff. I'm also going to be experimenting with temporal lags, which basically means that you're going to be looking into the history, let's say in the past month or 3 months, to predict flooding for the next month. My mapping is also done monthly to annually, like I talked about, which is unexplored in literature and also harder to do because these climate patterns are more spread out over time. Finally, my project focuses on pluvial flooding, which occurs when heavy rain overwhelms drainage, particularly in urban communities. This is often more difficult to model versus river and coastal flooding, which have more defined environmental interactions. To solve this problem, I first tried to look for data sets that already existed, specifically for the northeastern US, but I couldn't find any, so instead I decided to make my own. Existing data sets are often limited because they don't have a combination of these static, dynamic, and these flood labels. Therefore, my comprehensive data set will include both static and dynamic predictors and map-derived flood labels. And I'll talk about how I merged the 3 data sets on the next slide. So my 3 input data sets. The first one was Era 5 land. This is climate data at a monthly resolution. So this is my dynamic data set. This includes variables like rain and runoff. My second data set is Merit Hydro. This is static terrain. So it's basically things like elevation and drainage variables around the world. And this is at a 90-meter spatial resolution. Finally, for the actual floods, I use the Global Flood Database, which is really cool because it has 2 types of data for each of the floods over the period of 2000 to 2018. The first are property keys, which act like metadata for each flood. Think about things like location, time, and the amount of people that were affected by the flood. But then, they also have bands, which basically when they use MODIS satellite imagery to check if pixels in the flood-affected area are either have water in them and how long they have water for. Now, like I said before, these 3 data sets are at completely different spatial resolutions. So think about it like all of them are on a grid, but the grids differ in how much the points have, are spaced. So I first defined the first data set, Era 5 land, as the base grid because it has the most coarse spatial resolution. Then what I did is I created a circle or a buffer-based radius above each point and averaged the values of the other data sets to create my final data set, which included a tabular output of location and time. For the flood data specifically, when I created that circle, I first looked, are there any flooded pixels, which is the bands from the Global Flood Database? And if so, I set a binary flooded value to 1. I also computed a novel flood magnitude index, combining 3 different things. First, the percentage of the area that's flooded around the Era 5 point. Second is the average severity of the pixels. And third is the average duration of the pixels. Now, because we're using machine learning models, there are a couple of targets that I wanted to look at. First, you can see that like a lot of these equations have like TP and FN and things like that. TP is true positive, so basically when the model predicts a positive flooding event and it was correct, while false negative is when it predicts a negative and it's incorrect. I want to look at some metrics that are specifically used for binary classification, so when you predict 1 or 0. And some of these include ROC AUC, which you can see an example of a curve here where a higher number is better, and I aim for around 0.8. And also lift, which when you take this PR AUC curve, find the area under the curve and divide that by the class imbalance ratio. Some additional considerations I have is first creating a novel risk metric, which basically checks what percent of floods is the model able to capture in the top K% of predicted risk. Then I also want to deal with class imbalance because floods are inherently super spread out over time. So this can be done with methods like sampling and loss. And finally, I want to test if my predictions from the Northeast can transfer to other countries around the world. So with all this in mind, this is what my overall model pipeline is. First, we take those 3 data sets, combine them into the geospatial data set. Then, in feature engineering, like I talked before, we create climate lags and make sure that our static and dynamic variables are treated correctly. Now, we go into this 2-stage model. First, for stage 1, we use flood classification. So this is predicting either will there be a flood or will there not be a flood. And then, if the model predicts that there is a flood, this goes into a second model, which predicts that same flood magnitude index that I was talking about before. This will create a couple of risk maps for different areas in the Northeast. And then finally, I plan to add socioeconomic indicators to make sure that government investment is done equitably. A couple of the models I used. So first of all is an XGBoost model. So this basically combines multiple decision trees into one prediction. You can see an example of decision tree. It's basically when a model combines different statements that are either yes or no and chooses where to go based on that. So as you can see here, this model predicts flooding if there's been past flooding and precipitation is high. I also used an SCS-CN physics-informed neural network. And I know this equation is pretty complicated, but basically just know that this machine learning model is also guided by physics. So now let's go into my results. First, for stage 1, this was the flood binary classifier. On the left, you can see my model's predictions. The light red is the top 5% of predicted risk, while the dark red is top 1%, and the blue is the actual floods. You can see that my model is pretty effectively able to predict at least the western Pennsylvania and western New York floods in March of 2018 as seen in this figure. On the other hand, I'm comparing this to the FEMA maps, which are used nationally in our static, like I mentioned before. In the same exact month, it was pretty badly able to predict the actual floods that happened here because most of its risk zones are concentrated in these areas. Overall, my model had an ROC AUC of 0.9875 and a PR AUC lift of 71.3, both of which are higher than what I aim to get. Additionally, it captures 74.3% of floods within the top 1% predicted risk, which means that it's consistently able to predict high confidence for flooding events. Finally, comparing it to FEMA, it has over 10x improvements in different metrics that are used like precision, recall, and lift. Now going on to my stage 2 model, which was a regression model based on the flood magnitude index. Again, this flood magnitude index was calculated as the combination of the area percentage of the flood of the area that is flooded, the average severity, and the average duration. I first normalized this to a 0 to 1 scale to reduce the skewed target distribution and make it easier for the machine learning models to actually predict it. This is an example of the same month, March of 2013, when it predicts the severity for the positive predicted flood events. My model ended up having an R-squared of 0.93 and a Spearman P of 0.84, with over a 70+% decrease in mean absolute error over baseline. We want R-squared and Spearman P to be higher to signify a better model, and mean absolute error, or MAE, to be lower. Finally, like I said before, I kind of wanted to incorporate some socioeconomic indicators. So I found this data set called the CEC Social Vulnerability Index, which is really good because it measures how communities are able to respond to natural disasters and public health issues. Over here, I first did my stage 1 model, and then I multiplied this by these social vulnerability indexes for each county in the US Northeast. Dark red areas, which basically means that the flood probability was high and the socioeconomic vulnerability were high, are high hazard and high vulnerability, while lower areas may not be as important for the government to actually invest in disaster mitigation strategies. Then, using feature importance, I tried to identify key variables that help the model predict flood. So apart from pretty common static and dynamic variables like first location, elevation, which are commonly used to predict floods, as well as precipitation and runoff, I identified a couple of variables that haven't really been used in the past. The first is V10 and U10, which you can basically think of like vector components for wind speed, but all they mean is like how intense the wind is. Then SSRD is solar radiation, but that's actually more importantly showing cloud cover, which is usually used to like indicate if there's going to be a storm happening soon. Then I also identified snow melt and atmospheric moisture as things that are slightly related to precipitation, but are not the exact value of that. Overall, I noticed that these variables might have been more importantly identified in my model because my model uses a month before to forecast for the future. And these are usually indicators of like storms that are going to happen based on climate history. As you can see, I also separated the feature importance by color into static and dynamic. And you can see that both of them are important in their own ways. Additionally, I also did some additional analyses. So first, I did a statistical analysis at the beginning, and this basically showed that single variables are pretty highly proportional to actual flooding. For example, height above nearest drainage and precipitation. But it also showed the need to combine all of these variables into one model using machine learning. Additionally, I used sliding window validation, which is basically when I tested on each year separately by creating a new model and training on the past 5 years for that same model. And finally, like I talked before, because these data sets have very high class imbalance ratios, I use focal loss, which is a method to make the model focus on the very hard to predict locations and reduces the impact of class imbalance. So what were the conclusions of this? First, the two-stage model, which has rarely been done before because most other models just predict likelihood, allows for the model to flag both where a flood will occur, and if so, how severe it would be. Additionally, combining physics-based constraints with machine learning makes the predictions more accurate. Additionally, this can be generalized to countries around the world. In my case, I chose one country that is environmentally similar, Romania, and one country that is environmentally different, Myanmar, to test if my model is able to generalize in different situations. Some future work that can be done is first, in my data set, there is a very high fluctuation in the amount of floods per year. And this could potentially be to the fact that it uses satellite imagery to actually detect these floods. Cloud cover can affect the satellite imagery, so there's a need for more comprehensive data sets around the world that can be used. Additionally, ERA 5 land, which is my monthly climate data, would be delayed in real time. So I have to find a way to actually use that in real-time prediction. The overall significance of this project is that first, dynamic forecasts had a significant improvement over current approaches, specifically FEMA, which is what the national government uses to meaningfully to capture flood events. Additionally, testing monthly to annual predictions is a significant amount of time for governments to actually plan out where they're going to invest. And this creates different time frames and allows for success in different types of strategies. For example, just evacuating a community or actually implementing infrastructure that can stop these floods from occurring. My project can have a couple of use cases. First of all, it can be a low-cost and open-source way to inform government investment by integrating it with the current FEMA workflows. They're not mutually exclusive. Additionally, like the features that I identified as important for prediction, it can help us develop a better understanding of flood dynamics. And finally, the US Northeast can serve as a model template for other regions across the world. My long-term vision for this project is first, like I said, to identify a major validation data set to make sure that my model is actually practical in the real world. Then, I aim to collaborate with other nonprofit and governmental industries to actually put my model into place. Thank you.
Could you go back to the slide with they put the pictures of the upper northeast and the photo floods at?
Yeah. This one?
Yeah. So in the right picture, are those numbers also contributing to like the percentages? Because those are relatively high percentages, but I see that like those dots aren't necessarily in the correct places.
So you're talking about this picture?
Yeah.
Yeah, so that picture is the FEMA zones. It's not my own model. So basically what I'm trying to show here is that the FEMA zones, because they don't like accurately capture changing climate conditions, like let's say there's more precipitation due to climate change, it's not accurate in its predictions.
Okay. And that was a different time frame? The picture on the right to the picture on the left?
No, this is the same exact year. So you can see like the flood events are like shared between
Okay. Oh, okay.
Yeah.
Are there other student questions first? You go ahead, Derek.
Suvid, great presentation. I know like your prediction currently uses like previous year's data to predict floods in the future.
Yeah.
Are you able to predict floods in the past? And if so, like, how do you manage to do that?
What do you mean? Like take like current conditions and predict?
Yeah, and predict floods in previous years.
So I didn't really like train my model to do that because machine learning modeling is basically using current and past data to predict for the future. But I think like more importantly, like that wouldn't really be significant, right? Like we're trying to like give governments the opportunity to like predict in the future so they can actually make a difference and stop this flood from happening. But yeah, I guess that's pretty interesting.
Yeah, so you seem to use a two-stage approach to first predict where floods will happen and then the strength of those floods.
Yeah.
Have you thought about using an end-to-end prediction model instead?
What do you mean by that?
Like an end-to-end prediction model where your loss function is built off of location and off of the strength of the flood?
Yeah, so the reason I split it up is because the stage 2 model is only ran on positive events, right? Like the easiest way to explain it is that because my data set is imbalanced, the regression values would be 0 for like 99% of the data, and they would be like, let's say 0.5 or 0.9 for 1%. So that makes it really hard for the model to actually distinguish between like high severity events and low severity events. So that's why for like this stage 2 model, I split it into only training and testing on positive events, so it doesn't have like as skewed of a distribution. Does that make sense?
On your previous slide, you were just on there.
Mhm.
So it looks like your model is predicting more areas of flooding than the FEMA model is. Is more necessarily better? And how do you know that more is actually really going to be accurate? I guess then the follow-up of that would be like, did your model predict any places that FEMA predicted as positive as negative? Like, did it have any
Yeah, so
differences?
a couple things. So the FEMA, like the percentage of the total boundary that it covers is 2.8%. So first of all, you can see that like the dark red, right? Like that's the top 1% of predictions. So that's actually like a lower amount of areas covered. But when I like did this comparison here, I made sure that they were at the same spatial coverage. So like they tagged the same amount of locations to flood, right? Because we don't want to like tag too many areas because that just makes it too hard for the government to actually choose where to invest in.
Well, and I worry about like insurance, right? Like you
Yeah.
get flood insurance on your home, and these models are over predicting. The worry is that if it's over predicting flooding, right? Like all these people are being charged
Yeah.
money for insurance.
I'm sorry, what was your second question?
It was just that like, does the model like it looks like generally speaking, it's a lot more predicted flooding areas. Did it ever identify any model, any predicted flooding areas, or like the opposite of what FEMA said, like, or is it really just always more a bigger area?
So I mean they are like I know like this looks like it's less area, but technically when you like put them at the same I guess like grid, then it's not. But one thing that my model did, and I know this is not exactly answering the question, but the places that FEMA didn't identify, 95% of floods happen in those areas. So my model was actually able to identify them better. And then one thing I also did was that I overlapped the predictions, so I basically combined them, and I found out that the combined predictions actually worked even better than like any of them individually. So that's why I showed again, like it might even be better to like have a complementary based prediction.
Thanks for the great presentation. I was wondering, is it possible to use a model or some predictions of future, the global change, climate change that is going to happen, to incorporate that into a model to see, in the future
Like you're saying at like a
what
longer time
places are
period?
going to be affected.
Yeah, no, that's definitely a good idea. I think like given that right now my model is using the present to predict for the future, it's not as like focused on I guess like predicting for like the next 10 years. But like I know that there do exist like climate I guess like simulation models. So I guess that could be used with like these monthly predictions to actually expand them to a longer time frame. I think that would be pretty interesting.
I think we gotta get to classes.